But mainly I'll be talking about volume coupling and what I've been testing out in this kind of frame. So firstly, just to introduce the topic, I know not everyone is familiar with nuclear energy. I won't bore you with the details of fission chain reactions and so forth, but just to give you an idea of the fact that it's actually a very active field right now in what we call reactor analysis. This is both because people are working very hard to optimize existing operating reactors, doing, for example, these super high fidelity simulations of light water reactors that you can see on the left, and also exploring other concepts for kind of different applications or, for example, for industrial heat, as you can see in the middle. And the microreactors that I mentioned are the focus of my work. So what exactly do I mean anyway by reactor analysis? Basically, we're talking about modeling the reactor core, but also how that kind of interplays with other aspects of the power plant. But mainly, we consider the fact that we have a lot of different physics going on, and they're all fairly tightly coupled, especially when we talk about the neutronics, which is this fission reaction, and the heat transfer in the core. As well, we also might have to consider thermomechanics, and certainly in the case of microreactors, that's quite important. And we're dealing with a lot of scales. So in terms of length, the length scale goes all the way from about 1 millimeter when you're dealing with individual fuel pins, all the way to several meters in the primary and secondary circuit, and so forth. And timescale-wise, it's an even greater span, from about a microsecond all the way to several years. And the way that this has been handled in the past, with what we call legacy codes, basically they kind of make some conservative assumptions, or they kind of leverage some design-specific information. So for instance, with conventional reactors, you can more or less treat the flow as being mostly one-dimensional, and this is kind of the field that we call thermal hydraulics. And then they rely a lot on what I mentioned, the conservatism, but also experimental validation and operational experience. And then as far as the coupling, this is done basically between these fairly low resolution codes. So it's not especially challenging performance-wise, and the coupling implementations are typically bespoke and not very advanced in that regard. But nowadays, with these new challenges for modeling, there are new modeling code suites being used, and these are relying on kind of generalized solvers for various kinds of, for example, geometries or designs of the reactors that may use different coolants, etc. And so they use unstructured meshes, and they're high resolution, and they rely on the kind of PD frameworks that we might be familiar with, like, for example, OpenFOAM. And there's one that's very popular that was kind of purpose-made for these kinds of simulations called MOOSE. And in general, they're trying to be super high fidelity to overcome gaps in experimental data, at least in the short term. And furthermore, they're kind of made to do multiphysics already from the beginning. So the coupling is no longer an afterthought. But even though this is where we are, there are some important limitations still, which are kind of what I'm trying to address in this work. So first of all, these suites basically bring you to a sort of walled garden. So it's not very easy once you start using it, for example, a MOOSE-based suite, to actually introduce other solvers that use a different framework under the hood. And so because of that, it kind of forces you to stick with, in the case of OpenFOAM, a finite volume implementation, or in the case of MOOSE, a finite element. And also, it kind of allows people to develop closed source solvers, since they know that they can rely on the framework to allow you to do the coupling. But actually, we want to move away from closed source as well. So I started to investigate how we can use preCICE to alleviate some of these issues. And I encountered, of course, that there are some examples in the general field of nuclear power where it's been used. There was a previous talk at one of the preCICE workshops where it was used for modeling tokamak blanket for fusion power. That's on the left-hand side. And also, a bit more recently, people have been using it for analysis inside the containment structure of a nuclear reactor, mainly for basically analyzing conjugate heat transfer or understanding the dispersion of radionuclides. But as far as I could tell, there was no concrete example of people doing high-resolution volume coupling within this field, so it's kind of something that needed to be tested still. And in this regard, some interesting challenges for doing volume coupling for reactor analysis is that they're fairly large problems, at least several million cells in a typical simulation. And when you couple the neutronics to the thermal behavior or CFD, there's going to be a big discrepancy in the mesh size. And yeah, especially also the local resolution of the meshes can vary a lot. So the mapping is important. And in general, they're fairly expensive. So the more times you need to iterate in order to converge in a certain coupling window, the worse. So it's something that can really benefit from any acceleration. So then as far as my specific project, which is focused on microreactors and specifically these so-called heat pipe cooled reactors, it happens to be a nice testbed for doing this coupling with preCICE because they are physically small reactors and the meshes are smaller, so there's less of a performance overhead. And also, I don't need to do any fluid modeling, actually. So when it comes to doing the coupling, we stick basically with scalar fields. And that basically is because these reactors use heat pipes that internally have a two-phase flow of natural circulation, but basically this can be treated as a black box in some sense. So now I'll just describe some of the codes that were used in this study. So firstly, I compared two cases, there were two cases for studying the coupling. Firstly, I coupled a neutronics solver known as FEM-fusion. So this is a finite element tool which solves the neutron diffusion equation. And this was coupled with a very simple thermal solver in OpenFOAM, which just does heat conduction. And basically, in the case of FEM-fusion, it's actually written with DL2, but the DL2 adapter, at least at the time, was basically set up for surface coupling, so that was basically just used as an inspiration, and then the preCICE API then was implemented directly into the code to enable the volume coupling. And this flowchart just basically shows you a simplified schematic of how each time iteration is interrupted. But the code, essentially what it does is after a series of kind of more physics-specific things, it will give you a power density distribution, which can be passed to preCICE and then received by the temperature thermal solver. And the thermal solver, as I mentioned, is just a very simple conduction solver. And it uses the OpenFOAM adapter directly with the one small variation that since the adapter basically expects only certain types of physical fields, I just added this kind of generic power density field to the adapter. Additionally, we have this reference code, which allows us to make the basically benchmark comparison. And this is a code that we call Mambo. It's based on foam extend, and it does all of the coupling internally, but it solves the exact same equations as the other two codes that I just showed. And yeah, since it's OpenFOAM, it's just finite volumes. Okay, but then also having this reference code provides an additional opportunity because it's actually possible to decouple the subsolvers in the code and then recouple them back together using preCICE, which also allows us to do a more idealized benchmark, essentially. Okay, so I'll just share some of the results that we have so far. In the first case, this is one experimental microreactor, which was built not too long ago, just a few years ago in the United States, called Krusty. And I adopted this simplified geometry that you can see on the right-hand side. And then the idea here is to do a direct code-to-code benchmark, comparing our reference solver which, as I mentioned, does internal coupling in OpenFOAM, to the preCICE coupled system, which is the FEM-fusion OpenFOAM. And so then, firstly, in steady state, we obtain the simultaneous solution, and this just compares the temperature fields that are obtained in just one little section of axisymmetric section of the core. And this was obtained using just standard Picard iterations and the nearest neighbor mapping. But the results are basically showing quite good agreement. And then importantly, also tested the transient capability, so actually showing that the coupling, the implicit coupling is working properly, and so the simultaneous solution is actually obtained at each time step, doing the checkpointing and so forth. And this just shows, this is basically a reactivity insertion accident, where as we expect the power to increase and consequently the temperature, and the results from the two codes are in very close agreement. And just a note on the performance, it's in this case where it uses these simple algorithms, the nearest neighbor, it's basically negligible. There's no noticeable initialization time, or when it's doing the coupling, there's no significant overhead. It's not actually worth measuring it. Then this is moving on to the next case. This is a little bit more complex. So this reactor geometry is more heterogeneous, and this was a purely conceptual reactor. But as you can see, it has basically fuel pins scattered around the core, and then each one ends up with this little radial distribution of kind of a power peaking toward the edge of each little cylinder. And so this was a nice opportunity to test some of the higher order mapping. Particularly, I tested the radial basis function mapping, and also to try the coupling acceleration. So this is the dynamic relaxation, also known as Atkin, and the quasi-Newton-Anderson acceleration. So this shows the results from the mesh mapping study. Basically, what was done is using the, as a reference, mapping between two very fine, two identical very fine meshes. That's on the right-hand side, the reference. And then also doing a course-defined mapping with the two different algorithms. One is the nearest neighbor, one is the RBF. And that's using the partition of unity implementation, so it's fully parallelized. And basically what we find is, at least visually or qualitatively speaking, the nearest neighbor one, you end up with a bit of artifacts around the edges. This power peaking is not really represented super well, but with the RBF mapping, it's very nice and smooth, and qualitatively the results are very nice. And also when we measure the error, the sort of the L2 norm and so forth, again, it's a noticeable improvement. And then with respect to computation time, this time it's not imperceptible since it's using the RBF, but since it's fully parallel and so forth, the only real cost is basically at initialization. And for a kind of real problem with many time steps, it also becomes insignificant. Additionally, I also tested the coupling acceleration, as I mentioned, and this actually shows for a single transient simulation case, how does the wall time evolve when we tighten the coupling tolerance. And this, so we have 4 different cases of coupling tolerances, and for each one we run the same transient, which has many time steps, and compare the naive Picard iteration versus the 2 acceleration algorithms. And in all cases, we find a nice speed up from the acceleration, roughly 30 to 40%. And just a minor note here also, in all cases, the subsolvers have the same tolerance, respectively. So by the time you get to the tightest coupling tolerance, it starts to suffer a bit, and then it seems that the Anderson case is a bit more stable. So that's the kind of the overview of my focus so far in implementing in applying the volume coupling of preCICE. But there are some important plans for continuing to use the library in the future. So particularly to set up this kind of generic modeling platform for these microreactors, there's some other modeling needs that are very important. So firstly, the heat transfer models need to be improved, and that means that firstly you need to add radiation modeling, but also you need to be able to have the power be generated not only in, let's say, the fuel, but also at far field. This is a result of photon transport and so forth. Thermomechanics, as I mentioned, is quite relevant. The thermal expansion might be represented as some kind of simplified assumptions, but also the stresses are actually one of the main kind of failure points of these reactors, so that needs to be added. Then a dedicated solver for the heat pipe behavior is needed, and also altogether it needs to be coupled to some kind of balance of plant, or in the case of a propulsion application, what we call balance of vehicle. And what does that imply about using preCICE? So that means we need to do surface coupling to the heat pipe solvers. We plan to use this FMI coupling functionality since we'll do a dynamic system modeling using Modelica. So this will kind of tie everything together. We'll further test the kind of subcycling capabilities and time interpolation, since basically anything we can do to reduce the overall computing cost is valuable. Also, I became aware of this micromanager, which is quite interesting since we have all these simultaneous heat pipe solves. There's heat pipes distributed throughout the core. This could be quite nice as a way to handle all of these simultaneous runs. And also, as far as the higher order mesh mapping, before I tested radial basis functions, I actually looked into the linear cell interpolation, but I ran into a bit of issues there because, at least in this test case, it was the finite volume to finite volume mapping. And basically, when providing the mesh connectivity information, this didn't really work out so well. So actually, this is something I would like to potentially discuss in the user session. And of course, then when it comes to the thermomechanics, the mesh ideally would deform, and this will then need to be mapped to the respective solvers that will have feedback from this. And this is kind of, I have to say, kind of an end goal, which might not even happen in the frame of my project, my specific PhD, but we have an idea that this platform that I'm setting up is kind of long-lived, and perhaps this will be one of the last features of preCICE that could be implemented. So with that, I'll just say thanks a lot for your attention.
Thank you very much, Mario. Thank you very much. So are there any questions? Yeah.
You mentioned the coupling between preCICE and Modelica. I wasn't aware of that. Is that simply possible, or?
So Modelica allows you to generate these so-called functional mock-up units. And then there is an available, what they call the FMI runner in the preCICE package, which you can then use to do this FMI-based coupling. So actually, we're planning to use OpenModelica to stick with open source. But in principle, you could use Dimula or one of these tools. Yeah.
Thank you.
Sure.
There is a publication about this. You can find the QR code on the whiteboard. Next question.
Thank you. Sorry if I missed this. The RBF mapping for the volume you did the parallel version with Ginkgo, or?
I did not install any additional Ginkgo package, but
I think this is how it's described on the website, so I'm curious.
Yeah, I believe it was possible to run it in parallel without that.
Okay. But this is how you achieved like performance similar to nearest neighbor mapping then?
Yes, I don't think it would have been possible if it were not parallel.
Awesome. Cool. Thank you.
So maybe to clarify, so there are different ways to parallelize. So one is this partition of unity, where we have all these small clusters. And then in another project, we ported the normal RBF mapping to GPUs, where you could use Ginkgo. And yeah, what David also did as part of the dissertation is to combine both. But I think what you used is the normal partition of unity mapping with no GPUs.
Yeah, that's right. It was the standard PU RBF option. Thanks.
Next question. We have a lot of time.
First, a remark. So be aware the FMI runner, I would say it's in the state of a prototype. So it's not as developed as the OpenFOAM adapter. So if you start using it, please let us know what you're missing and maybe even contribute back if you are adding features. It should be fairly easy to extend, but currently it has a very minimal feature set.
Okay, will do. Thanks.
Yeah. And I was wondering for your the performance runs that you did, could you comment what were kind of the largest meshes and the largest MBI ranks that you used for the volume-volume coupling?
Sure. Yeah, it was not too many ranks. It was, I think, like 24 CPUs for these cases, and they were dividing up these meshes that were like 5 to 10 million cells, roughly.
And you used for both solvers the same domain decomposition?
Actually, so this case is showing just the one-way mapping of the neutronics information. So I guess it's not really relevant for that, but when I ran the coupled cases, I actually tested with a different number of ranks. So with the thermal solver, it's a much simpler or faster problem to solve. So I only used a couple of ranks and then a lot more for the neutronics solve. And this was quite painless actually. So, and I think as I mentioned also, this reference code that I decoupled and kind of glued back together, it's based on foam extend. So actually this ended up being excluded. I did not use the OpenFOAM adapter for this, but I actually found that it was relatively painless to get it running in parallel. So,
thanks.
I also wanted to ask on that. So for the foam extend adapter, for foam extend, for the code that is based on that, you just directly used the API.
correct.
Okay.
Yeah, so I was aware that there was some form of a foam extend adapter, but I assumed it would not work since it was at the time I started this was a little while ago, and this code is based on foam extend 5.
How hard coded is it to the specific application?
Fairly,
Okay.
I have to say.
Okay. If you have feedback that we could use for the more general, that would be a valuable contribution as well.
Okay.
Another valuable contribution.
Sure. Yeah, I mean, there are some little differences between, let's say, the foam extend API versus the standard OpenFOAM, the ESI OpenFOAM. And so, yeah, I did notice these when implementing things, but it was nothing too crazy to overcome. Yeah,
Thank you.
thanks.
Any other question? Not, then I suggest let's close it here. Thanks again once more.
Thank you.